introduce Professor Liliane Barrichello from the Department of Mathematics in the Federal University of Rio Grande do Sul. Liliane is very well known for analytical solutions of the equation of radiative transfer that, well, this is how we in heat transfer call it, but it's, that has much broader applications than only heat transfer. And so it's a great pleasure to have you here, Liliane. Please have the floor.
Thank you very much. Can you hear very well? Thank you very much, Elcio, first of all, for the invitation. And I also thank all the organizing committee for the opportunity of being here. And good afternoon. So the idea here is to talk a little bit about inverse problems in this field of transport theory. There are some, in particle transport, there are some inverse problems of particular interest and relevance. Maybe I could say actually some classical inverse problems in this field, which are related to, for example, nuclear safety, where people are interested in the source detection, in the detection of some radioactive source. Another classical inverse problem is related to optical tomography, for instance, where the reconstruction of the absorption coefficients in the equation can bring us some important functional informations, for instance, about brain, for example, that can relate some diseases can be related to the behavior and the reconstructions of the absorption coefficients, which are parameters of the main model, in the case the transport equation. So right now, our work is related in different ways with these two different problems. Different ways. One of them really is the focus of our research, which is, for example, the solution of forward problems, which are basic for describing, for example, the case of the optical tomography, as Elcio mentioned, the radioactive transfer equations, and where we are interested as much as possible in deal with analytical approaches to deal with this forward problem that we expect that later will be somehow associated with some inverse technique, which is part of the optical tomography process. In particular, this problem, this study is a joint work with one of my PhD students, Karine Rui, from the graduate program of mechanical engineering in my university, Federal University of Rio Grande do Sul. Another approach is more related with this conference, where we are trying to work a little bit in this issue of source reconstruction. And in this case, this is a joint work with another PhD student, Cássio Pazinato, from the applied math graduate program of the same university. In regard to this, the use of or the study of some inverse techniques for source reconstruction, our particular interest in this case is on the use of the adjoint operator of the transport equation in the solution of the inverse problem. We start with some medium where we know the physical properties and the geometry, and in this preliminary case, one-dimensional medium. And we also start to work with that, not just because you are interested in the application itself, but you see, I'll try to explain a little bit. We have worked some years ago in one of these approaches that we call analytical discrete ordinates method to solve the forward problem. And so we are interested in use that formulation to develop also analytical solution or explicit solutions for the adjoint flux, for the adjoint operator, and then try to use that somehow in the reconstruction, the search reconstruction. What we were trying to find, of course, was some computational time, computational game in terms of time that we know in general the analytical solutions can help in regard to this issue, and because that this work has a lot of use of what we call mathematical methods, and so in the case of the search reconstruction, in using this kind of analytical solutions for the forward and the adjoint flux, one point was also the construction of the particular solutions, what we did using Green's functions. So these are some interested, and then we start to work in this problem. In the second aspect, which are the forward problems related to the reconstruction of the absorption coefficients, as I mentioned before, our focus is in the solution of the forward, the 2D transport equation. We have developed some formulation, I'll talk a little bit later, for the transport equation in neutrons applications. But now, if you want to use that for the specific case of the optical tomography problem, since we work with analytical methods, we have to rederive and develop some specific aspects of the solution to apply in these tomography problems. So that's the idea of our main goals. So in this talk, we report some studies and preliminary results we have carried out in this contest. Basically, I'm going to talk about the search reconstruction problem. And in this case, what we want to estimate are the coefficients of a proposed expansion of the search term in the equation. We worked with what we call isotropic search. And we consider two different kinds of searches, the polynomial search and piecewise functions. And we have used this, basically the Tikhonov's regularization to deal with the Wilposness of the problem. The other part I will just mention a little bit at the end. It's not going to be the focus of the presentation. But since I was not sure, I mean, probably the audience will not be so familiar with the model that we have to work. I thought it would be nice to show what is the fundamental forward problem when we deal with this kind of applications. That's in this case, is the neutron transport equation. That's an integral differential model. Of course, in this case, here is the inhomogeneous search term that I want to reconstruct. And we have here some important terms in this model. That's what we call the streaming term, and the terms related to the collisions. I mean, that comes from a balance I'm going to mention. I'm going to mention just after that. These terms are related to a balance in what we call the phase space. For example, when I'm going to try to describe a particle, I have to consider a balance in the particle which is in a position R about this differential element dV. And, sorry, that's not working very well. In a direction gamma about this solid angle around omega. And I have to consider then the directions of the particles will be considered in the whole unitary sphere such that I have to deal with two different coordinate systems. So one in terms of the position of the particle and another one in terms of the direction of the particle. So from here I have 6 variables, and if I don't consider a stationary problem, I would have 7 variables, which will be the time. And a classical approach is to treat the variation of the angular direction in discrete directions, which we in general call the discrete ordinates method. So in the discrete ordinates method, the scattering term that I have here in the right-hand side, it's treated in terms of a numerical quadrature scheme. Here, this parameter, it's called, for neutron, it's called total macroscopic cross-section, which has to do with the probability of interactions. For example, when I'm dealing with the tomography problem, I have here what we call the extinctions coefficients that includes absorption and scattering, which one of the parameters that we want to, in general, reconstruct in the tomography problem. What here I call the differential scattering macroscopic cross-section that somehow describes how the particles interact. Again, for radioactive transfer problems, I have to deal with different forms of interaction, and in those problems, I have to deal with high order anisotropy than, for example, when I'm talking about neutrons. So it's not just a question of changing the name of the parameters that are involved, but depending on the problem that I am interested, also some aspects of the model are more important, like anisotropy or, for example, the absorption coefficient. And so for this problem here, this psi is the angular flux in some position r along direction omega, as I mentioned before. Okay, so if I consider a very special case of this problem, a one-dimensional case in the spatial variable, stationary, like I have this problem already, I will, for example, in a slab, in this case, a multi-layer slab, I suppose that I have here different regions, and in one of the regions, in this slab, I have a detector which, with absorption cross-sections, I call sigma d. So first, the forward problem now for one-dimensional case, so a simplified form of the equation I had before, and here the scattering function, it's already written in terms of, expanded in terms of Legendre polynomials. The problem is simpler than the one that I presented before, but again, I have here the angular flux of particles. This is the cosine of the polar angle related to the direction of the particles. I consider the slab with the, thickness Z0, and the other coefficients I already mentioned before. So for this problem, I consider boundary conditions. That means that I know some incoming fluxes on the boundaries. And for this case, I consider here also some reflection, specular reflection. So when I have the detector with absorption cross-section sigma d, I can evaluate this measure, the rate of absorption, in terms of this expression, this inner product, which depends on the angular flux. Okay, so R is, measures the absorption rate of neutron particles within the detector's region, migrating from all possible directions. So if I know the solution of that equation, and I want to evaluate that absorption rate, I have to evaluate these integrals as are defined here. But the solution of the angular flux depends on the solution of the problem. And if I change in this problem the source, as I will see, I have to anytime reevaluate the flux to get this, the absorption. So I can use the adjoint operator, which for this case is defined in a very similar way. We don't have, it doesn't change very much from the forward problem. And I also can write the rate of absorption in terms of the adjoint operator. In this case, when we have this evaluation, if I want to calculate the rate of absorption and I change the source, I just have to compute the adjoint flux once. So if I change the source, it's easy to get the rate of absorption. So that's why we are interested in evaluate the adjoint flux. So, our first goal here was to get an expression using some analytical tools to get the adjoint flux for this one-dimensional problem. Also, we see that when we define the adjoint operator, we can, that's a kind of, it's not a physical problem in this case, but then we can choose some specific boundary conditions that are going to make this expression simpler in the sense of to evaluate that, which I need to get the rate of absorption, the R. I need this P. Oh my God. So if I get this expression simpler, and I see here that depends on the incoming flux, which I consider is known in this problem, and also the boundary conditions of the adjoint problem. Okay, so that's part of our work, which is developed, try to get some expressions for the solution of that adjoint problem I just formulated. And so we use here, and I'm not putting the details here, but we propose kind of a spectral method such that after some algebraic manipulation, we are able to get a solution for that problem, which is explicit in terms of the spatial variable in the one-dimensional case. So this solution is written in terms of eigenfunctions and eigenvalues. We derive this problem. And one interesting, I mean, this matrix that define the eigenvalue problem depends on the quadrature scheme that I used to discretize the angular term of the integral term of the integral differential equation. And the choice of this quadrature scheme, it's kind of relevant in the derivation of the eigenvalue problem. So one of the good features about the method that you proposed some years ago was that we are able to develop an eigenvalue with size half order of the number of directions. That was something different from the methodologies that were used before, and that give us very good results in the solution of many problems. And we were able to do that again here for the solution of the adjoint problem. So I have an expression for that adjoint flux, and that expression, if I will need, I don't think maybe it's not well written here, but again, to evaluate the rate of absorption of one detector, I need the solution. And to relate the solution of the adjoint flux with this R, I have to solve an inverse adjoint flux where the source is equal to the absorption of the detector. So when I'm going to solve this problem, I have an inhomogeneous, I have a source in the problem for the adjoint flux. If the source is constant, it's easy to get a particular solution since I can guarantee that these parameters are such that the denominator is different from 0. But if I have a more general source term, I need to define a particular solution, which we're able to do using some Green's function. And the particular solution was written in terms of the eigenfunctions of the homogeneous problem. So to evaluate this particular solution, as you see here, I have some coefficients that depends on the source. And all these procedures in the implementation of our solution, when you are going to see the results later, we somehow try to deal with analytical constructions as much as possible. Like, for example, analytical solutions, analytical calculations of these integrals instead of using numerical quadratures. Okay, so how we are going to use this kind of result in the source reconstruction strategy? So we consider a set of deep particle detectors in our physical domain, which is that slab. For each detector, we solve this problem where the source term for the adjoint flux is the absorption coefficient in the detector, the absorption of the detector. We suppose that we can expand that source in terms of an appropriate form, in terms of a basis function that we are going to choose. And then we want to reconstruct these coefficients that we call alpha j. Okay, in this work, in general, we choose the basis functions like sexually constant functions, like, as defined in this way, in some partitions of the domain. So what we do? We substitute in the rate of absorption the expansions of this of our source term, such that you are able to get a linear system to describe the coefficients that we want to obtain. The matrix of the system is based on these inner products of the adjoint flux and the basis functions. And again, here, as much as possible, we evaluate these things analytically. So here we are going to rewrite, as I said, we try to solve this, to get this coefficients in a kind of, I believe, straightforward way here for this audience, which is trying to minimize this expression, the objective function. And we are going to consider later some noise in these readings. So that's what I made this change here, where that's the exact measurement, and then we're going to consider some noise. As I mentioned before, we try to use Tikhonov's regularization here to deal with the Will conditioning of the problem, where in this case we took this lambda based on the Morozov principle. So our first test was this polynomial source. For the domain was thickness 10. And that means we have a high scattering in the problem. And the anisotropy is also, I mean, it's not so big, but L equals 6, we consider some anisotropy. And we consider that we have no incoming flux in the problem. First test, we consider 10 detectors distributed in the physical domain. And the absorption cross-sections of the detectors were defined also kind of a sexually constant way. So for each detector, to get this, what we call exact reading, we did two things. First, we solved the forward problem with our analytical solution, but with, I mean, not very high quadrature order, which means that probably our result does not have many significant digits. That was already to impose some noise in the readings. But later we also applied the white noise in these readings, and we performed 5,000 different tests to the problems. So here we can see, for example, the idea of the measurements errors imposed on our readings on these 5,000 tests, and the results that we obtain if you consider two different partitions, 10 and 20 partitions to establish the basis functions, the domains of the basis functions. Here we have the S hat, which is the solid lines, the reconstruction, the source reconstruction we have in this case. The figure indicates that we're able to reconstruct, at least to recover the shape of the source in this case. But we also try to evaluate the difference between the relative errors, in the exact readings and the ones that we are able to obtain when we use the reconstructed source to solve the forward problem after we ended the reconstruction. So what we have seen here for these kinds of tests, that we're able at least to keep the error in the reconstruction as the same behavior order of the error that we impose in the measurements. And here we have some data about the Tikhonov's parameter that we used in this reconstruction. Then we consider that localized, piecewisely defined source, again, some different parameters. Now the domain has thickness 30. We also consider the absorption in the detectors like defined, sectionally defined. And we distribute 60 detectors in this domain. Again, here we have the distribution of the error. I mean, in terms of these 5,000 different tests we execute. And here the reconstruction, the S hat, again, solid line that we were able to reconstruct for the source. We actually use different partitions here. But in general, for example, we use later 60 measurements. I go a little bit ahead. For example, we consider the case where you have the detectors more concentrated in some region. We also consider the case where we don't have the same number of detectors than the partitions that you have defined for the domain. In all cases here for this kind of problem, it seems that we did not get much better for considering for increasing the number of detectors of measurements to reconstruct the source. I think that's what I just mentioned here. So for this problem, the test we performed, it was in this i5 Intel Core processor with 16 gigabytes, and we used some MATLAB subroutine to solve the non-negative least squares problem. And that's a kind of average of computational time we took for the different tests that I showed here using this kind of approach. Then we went for a little bit more complex model, still a one-dimensional model, but now we consider the energy dependence of the particles. So here, we basically have a kind of a vector version of the previous equation, where now we have matrices here that include those parameters like macroscopic cross-section and scattering, like scattering parameters. And in this case, same kind of boundary conditions I mentioned before. Multi-layer slab, where I use then the particle, the detector in some region. We have to rederive that expression for the absorption rate, that kind of trick in terms of the energy dependence. And you are going to try to use the same procedure we did before. The only thing here, let's see. Again, we developed a solution for that vector problem, which is analytical in terms of the spatial variable. And we rewrite the absorption rate in terms of the solutions we got. And as much as possible, as I mentioned before, we evaluate these inner products. Here I have the dependence on the basis functions as much as possible in an analytical way. First, another test we did, I did not show in the other case, was we compare like the rate of absorption that we obtain solving the direct problem with the one that we obtain using the expression for the adjoint problem. So here we see that when we increase the number of directions, if we use explicit formulas, we are able to obtain very good precision when we compare these two. And when we try to implement those inner products using some kind of quadrature scheme, we lose a little bit this kind of accuracy. And so, I mean, it's still the method, it's very fast to solve this problem. So it was just to check the kind of results that we see. We get lots of digits in agreement as much as we increase the number of discrete directions that I explained in the beginning. So we try to reconstruct the search also using the same procedure we did before, expanding in some known function. And so now we have to consider the different levels of energy. And here are some of the expressions we have to evaluate. And as I said, these are expressions in terms of the eigenfunctions and eigenvalues. So that's the system that we get for the coefficients are written in terms of these matrices, which we try to evaluate using the expressions we developed now for multi-group case. We do the same thing we did before. We consider the exact readings, and then we consider some additive errors. Same idea than before, just here the notation is a little bit different. But for the linear case, like it's the case that we have here, we solve using least square method. Now we have this data was taken from a direct problem that we have solved before for the two groups of energy. Again, we use the Tikhonov regularized solution. And let's see. We also consider to add more noise to the readings. We solve the problem using a numerical method that we suppose we don't have exact solution as good as before, already for introduce some noise in our data. And the metrics of the problem that you solve by least square, we evaluate using the analytical procedure I mentioned before. And here are the perturbation that we consider in both cases, same like we did before, 1% and 5% of the standard deviation. Now we have a search for group 1 and group 2. That's just a two-group problem. That's the results we have when we impose just 1% of the error on the previous readings. And that's the idea of a comparison between the exact absorption rate and the perturber one, the kind of data that we have used to reconstruct the source. That's what we got in terms of the source. In this case, this example I'm showing here is just a localized source. Here we put some results about the absolute error in the exact and reconstructed source, and also relative error. And that's the flux, the reconstruction of the flux in both cases. Then when we increase a little bit the noise here, we see already some difference, especially in group 2. And also, we see, for example, here that we keep the same absolute error, but then we increase the relative error that becomes bigger than the error that we impose in the measurements. But the flux, in general, we are able to reconstruct in a good way. So we consider, in general, that the method was successfully applied for simple reconstructions of one-dimensional problems, including energy dependence, as we could see, even with some imposing some perturbation. For the one-group case, we always, for those tests, we were always able to get errors slightly inferior to the noise that we added, except for the example of the group 2. The solution is fast in both cases, and we actually have already implemented that using also the Bayesian inference, the Metropolis-Hastings algorithm, but I thought, we just got those results or kind of analyzing, but I thought we should not, I decided not to show it here. And of course, here, in terms of the source reconstructions, not just, here is written to try to alternative forms of dealing with these errors, like we did, for example, taking the statistics approach. But there are many things to be explored here, like the basis functions, the number of basis functions that you use. That's, but our idea is really, first of all, try to improve, that's what our focus, try to improve the solution of the forward problem, mainly in terms of being able to solve as much as possible using analytical tools, the forward problem with more complex models, instead of working on the inverse procedure, actually, And so that's the idea also for the problem that the direct problem you are using, trying to solve it for the tomography. We have a formulation that is able to deal with some quadrature, alternative quadrature schemes, which we have seen in the literature. It can be important in the codes that are used to estimate the coefficients. And that's what we are working now, of course. I think that's a good point. That's what we are doing, but I'm sure that's a good place to have new ideas. So I thank you again for the opportunity of being here. I'm sure here people can have much more, many more suggestions for this kind of work, especially in the reconstruction problem, which we consider we are much more users than the proposing inverse techniques. So I'd like to thank again the organizing committee and people, CAPES and other CNPq and our university that provide some financial support to our work, some reference, and thank you very much.
Thank you.